So suppose you have data. Yeah. So step 1, you do the regression. Yeah. You do the regression y is equal to alpha plus beta xi plus e. Then you obtain pi hat square. You think that the variance of xi, variance of pi, is some function of z1, z2, z3 or some variable, right? So variance of xi, the variance of pi is some function of z1, z2 and z3. These are 3 variables it depends on. Right? It's not constant, it depends upon some 3 variables, z1, z2 and z3. So what we do is, you regress E hat I square on A naught plus A1 Z1I So you will do this regression where you use E hat I square as an estimate of the variance of sigma 1 square, E hat 2 square as an estimate of the variance of sigma 2 square and so on. Are you getting this? Sure? Okay. Once you do this, then, so you have a regression model where E hat I square are the dependent variables and Z1, Z2, Z3 are the independent variables. The null hypothesis of homoscedasticity, the variance of the error term is constant. The alternative is that the variance of the error term depends upon Z1, Z2 and Z3. How will you test that? How will you test that null hypothesis?
So Z1 is equal to Z2
is equal to 0. So if Z1, Z2, Z3 are all 0, then sigma E hat I square is alpha 0. A0. It is a constant. It doesn't depend upon Z1, Z2, Z3. So we test for the null hypothesis H naught A1. Yeah? Against the alternative I. Pardon? You can't read? Now? Either of the AIs not equal to 0. So if at least one of the AIs is not equal to 0, then clearly sigma hat square I depends upon Zi. So null hypothesis all the A1, A2, A3 are equal to 0. How do you test this null hypothesis? You have to test a restriction on Z1, Z2, Z3. No? How do you test those restrictions? Think. Just throw some answer at me. I won't throw it back at you if it goes wrong. Don't worry. अपने को टेस्ट करना है कि A1, A2, A3 are all equal to 0 against the alternative one of them is not equal to 0. अपन ने restricted और unrestricted regression कुछ किया? Can somebody explain? Can somebody answer Harsh's question? Why do we take A1, A2, A3 as all equal to 0 in the null hypothesis? Because if all, then so it will say that if A1, A2, A3 are all 0, then expectation E hat I square will only be alpha 0. And expectation E hat I square is sigma 1 square, sigma 2 square, sigma 3 square. So that will actually mean that sigma 1 square, sigma 2 square, sigma 3 square, sigma 4 square, so on. We are setting all of them to be a constant number. Right? If A1, A2, A3 are 0, then you just have the model E hat I square is equal to alpha 0 plus EI. So expectation E hat I square will be equal to alpha 0. So the expectation of E1 hat square, expectation E2 hat square, expectation E3 hat square, all of them are equal to sigma square, which means there is no heteroscedasticity. Right? They just depend on the unbiasedness of the estimators. Right? So now I want to test that null hypothesis. Everyone understands why that's a null hypothesis now that we are testing? Right? See, if the model is, if alpha 1, alpha 2, alpha 3 are all 0, what would this model be? E hat I square is equal to alpha 0 plus EI. Right? If A1, A2, A3 are all 0. Right? If A1, A2, A3 are all 0, then this model will be what? E hat I square, I must put a hat. E hat I square is equal to A0 plus EI plus some error term here. A0 plus EI. So what will be expectation E hat I square? What will be expectation E hat I square? A0, no? Expectation E hat I square will be A0. What is expectation E hat I square? Variance of E hat I, which is sigma square I. So we are saying sigma square I is equal to A0. A0 is a constant. So sigma 1 square, sigma 2 square, sigma 3 square are all equal to A0. That's what we are saying when we impose the restriction that A1 is equal to A2 is equal to A3 is equal to 0. Right? Whereas if any of the AI is not equal to 0, what does that mean? That sigma square I depends upon Zi. Right? Sigma square I depends upon Zi. Everyone is getting this? Shock? Right? So how will you test this null hypothesis? How will we test this null hypothesis? Think of restricted and unrestricted regressions. अपन ने किया है ना? We did, no? We did? Did we or did we not? We did? Okay, so it's high time we did this. Okay, so it's high time we did this. So suppose I have a regression model yi is alpha plus beta 1 xi plus beta 2 x2i plus e. Okay? And suppose I want to test the null x naught, beta 1 is equal to beta 2 is equal to 0 against the alternative either of beta is not equal to 0 against the alternative, and I think this will be so my null is that beta 1 and beta 2 are both equal to 0 against the alternative that either one of the beta is not equal to 0. So my null is that the conditional mean of y is a constant term. Doesn't depend upon x1 and x2. The alternative is that it depends at least on one x. You see the same problem being tested here. So the framework that we use for this can be used for this. Okay. How do you use the framework for this? Assume first that all the error terms are normally distributed. Assume first that all the error terms are normally distributed. Right? So one way of doing this, to say that the error terms are normally distributed. So first, estimate the regression with beta 1, beta 2 is set equal to 0. So estimate the regression beta 1, beta 2 equal to 0. That is, yi, just estimate this regression. Y is equal to alpha plus ei. Right? So what is alpha hat? What is alpha? Conditional mean of yi is equal to alpha. Right? Sure? What would be the estimator for the conditional mean of y? The mean of what is the estimator for? So we need an estimator for alpha. No? So what will be the estimator for alpha? If alpha is equal to the expected value of y, what is the sample counterpart of the expected value of y? Mean of y. So you would say alpha hat is equal to y bar, right? You would say alpha hat is equal to y bar. Can you prove it to me from our usual formula? X dash x inverse x dash y. Because then your design matrix will be, so if you have y1, y2, y3, say y4, y5, yeah, is equal to 1, 1, 1, 3, 4, 5, right? So this is an X matrix, huh? Your X matrix is 1, 1, 1, 1. And this will be P1, P2, P3, P4, P5, right? So what is X transpose X now? If this is X, 1, 2, 3, 4, 5, this is X transpose. What is equal to? No. 1 plus 1 plus 1 plus 1 plus 1, 5. Or in general, it will be n, right? So x dash x will be n. Right? What is x dash y? X dash y के लिए क्या करेंगे? y1, y2, y3, y4, y5. So x dash y is summation y. So x dash y upon x dash x will be what? Say x dash x inverse x dash y. X dash x is just a scalar number. So its inverse is 1 upon that scalar number. So x dash x inverse is 1 upon 3. And what is x dash y? Summation y. So what is summation y upon n? Y. Right? So what we are saying in this kind of a model is, essentially, when we specify a model like this, we are saying that yi is equal to alpha plus ei. I am saying the condition mean of y doesn't depend upon x. Each value of y is the mean of y plus or minus some random error. It doesn't depend upon x, right? As you know. So, if I now estimate alpha hat by y bar, I have an estimator for this model. I have an alpha hat. No, I just have to need to estimate alpha hat. So, yi hat is simply alpha hat, which is y bar, right? Alpha hat is simply the estimate for alpha hat is the average value of y bar, right? So now think of summation e hat I squared, yeah, upon n minus 1. What did this mean? Summation e hat I squared upon n minus 1. What is that? No? Isn't it? Because this is yi minus y hat square, no? But y hat is nothing but y bar. Yeah, it's the variance of y, but the variance of y is nothing but the variance of the error term, right? It's the sample estimate of the variance of the error term in the under the restricted regression. Yeah? So I will say sample estimate of the variance of the error term under the restriction. Alright? Sure? Sample estimate of the variance of the error term under the restriction. Let the population variance be S1 square. Right? Let the population variance be S1 square. Okay? Let the population variance be S1 square. This now is a chi-square distribution with n minus 1 degrees of freedom. Here is the sample variance divided by the population variance into the degree of freedom from a normally distributed variable. You assume that the error term is normally distributed. The chi-square is n minus 1 degrees of freedom. Similarly, I do this regression also. Let us call that the unrestricted regression. What we have below is the restricted regression. What we want to talk is the unrestricted regression. Okay, what we want to talk is the unrestricted regression. Otherwise, what we have below is the restricted regression. Sure? Okay. So now, similarly from this regression, so I will call this restricted regression, say I will call this unrestricted regression. They are the sum of the squared errors from the unrestricted regression. First we did was a restricted regression because we put the restriction, beta and beta is equal to 0. It was a restricted regression. Now we have the unrestricted regression and the sum of squared errors from the unrestricted regression. This, because 3 parameters are being estimated. Because 3 parameters are being estimated, this is nothing but SH square upon unrestricted regression, SH square of the unrestricted regression, the sample variance of the error term of the unrestricted regression, right? Sample variance of the error term of the unrestricted regression. Sure? Okay, now, so divided by S2 square, okay, and multiplied by n minus 3. This is a chi-square with n minus 3 degrees of freedom. Right? No, because alpha, beta 1, beta 2, 3 parameters are being estimated. So we put up 3 restrictions. Alpha 1, alpha, beta 1, beta 2. Right? Okay? Now, so let's understand this. What is this? This will be equal to summation can you see why? This part will only be summation E hat I square R, summation E hat I R square, right? Why? Because n minus 1 in the numerator, n minus 1 in the denominator will cancel out. Huh? N minus 1 in the numerator, n minus 1 in the denominator will cancel out. Sure? Okay, so this is this. Right, so this part is this. And this is chi-square with n minus 1 degrees of freedom. Sure? Similarly, you would have upon, sorry. Yeah? Will be a chi-square with n minus 3 degrees of freedom. Right? This part? Sure? Because, you see, this is SR square. This whole thing upon sigma square is a chi-square. Right? So if you multiply this pi by n minus 1 again, this n minus 1 will go now. Right? Understood? Right. So what it means is in black and white is summation E hat square un upon sigma 2 square divided by n minus 3 is a chi-square distribution of n minus 3 degrees of freedom. Right? N minus 3 degrees of freedom. Sure? If I subtract from it, what I am doing is I am subtracting the chi-square. Basically, so basically, or look at it this way. This is a chi-square distribution with n minus 1 degrees of freedom. The chi-square distribution n minus 1 degrees of freedom. If I subtract from it, so I have a chi-square n minus 1 degree of freedom minus a chi-square n minus 3 degrees of freedom. Yeah? I have a chi-square n minus 1 degree of freedom. I have a chi-square n minus 3 degrees of freedom.
So why are we dividing it by n minus 1 and n minus 2?
Because for a chi-square, you have to basically, right, at the moment we should not, right? Okay. But suppose I think of this chi-square. So this is, that's right. So if you have a chi-square, this is a chi-square n minus 1, you like that. The chi-square minus 3. So n minus 1 minus n minus 3 will be a chi-square with what degree of freedom? You're right, I was jumping now. Yeah? Is a chi-square with how many degrees of freedom? Chi-square n minus 1 minus chi-square n minus 3. Suppose n is 100. Then you have a chi-square with 99 degrees of freedom minus a chi-square with 97 degrees of freedom. So what will the resultant of chi-square? 2 degrees of freedom. A chi-square 9 degrees of freedom minus chi-square 7 degrees of freedom is a chi-square with 2 degrees of freedom. So this is a chi-square with 2 degrees of freedom. I'm just coming to it. Now, under the null hypothesis, so if you, what is the null hypothesis? Beta 1 and beta 2 are 0. Beta 1 and beta 2 are 0 is the null hypothesis. Which means that in reality, the null hypothesis says that there should be no difference between the restricted and unrestricted regression, because beta 1 and beta 2 are actually equal to 0. So if you do a regression with a restriction or without a restriction, it should not matter. Because indeed beta 1 and beta 2 are 0. Right? So if you are doing that, then the variance of the error term sigma, we had once, so the variance of this, the distribution of the variance of the error term in the restricted regression and the variance of the error term in the unrestricted regression must be the same, because the basic regression is the same. Because the null hypothesis is true, there is no difference between the restricted restricted and unrestricted regression. So both the variances must be the same. Right? Both the variances must be the same. Is this clear? Yeah. Why both the regressions, both the variances the same? Any idea? Yeah? All four of you, any idea why the variance of the error term must be the same if the null hypothesis is true? No? Okay, can somebody help them? Why am I saying that the variance of the error term must be the same for both the regression, the restricted and unrestricted regression, if the null hypothesis is true? Can somebody tell them? Any guesses? Yeah.
So we take it unrestricted, but we have beta 1 and beta 2 there. But if we consider the null hypothesis, we are always considering beta 1 and beta 2 both equal to be 0. So even in that case, if beta 1 and beta 2 both are 0, then it doesn't matter if we calculate it by means of unrestricted or restricted.
Exactly.
We have the same error term and thus the variance will also be the same.
Exactly. So what he's saying is, if the null hypothesis is actually true, then beta 1 beta 2 will anyway be true. Whether you include them in the regression or do not include them in the regression. Right? So the variance, the error terms will be the same in both the cases. And therefore the variance of the error terms will also be the same. Right? Sigma 1 square. Right? So let's call this, so it will not be different sigma 1 square and sigma 2 square. Both will be sigma square. If I say both are sigma square, then I can rewrite this as 1 upon sigma square, right, summation, we had I square r minus summation. Yeah, I can just take that sigma square out. Then common sigma square, right? Common sigma square and take it out. Sure? So I have here, let me write this again, 1 upon sigma square, summation, E hat I square. Yeah? This should be a chi-square with 2 degrees. Here is n minus 1 minus n minus 3. The chi-square with 2 degrees. Right. Now, this is not useful to me, because I do not know what sigma square is. I do not know the value of sigma square, so I cannot calculate this statistic, so I cannot take any test of it. I cannot calculate this statistic, I cannot take any test of it, because sigma square is not known. Right? So how do you then